Introduction and relation between these three error functions. So basically here I have three error functions. This is just the error function. First one is the normal error function. Second one is known as complementary error function. Yeah, because that's just complement to the first one. First is from 0 to x and this is from x to infinity. Yeah. So complementary error function. And the last one is imaginary error function. Yeah. And the name imaginary is because if we substitute t as minus t and then sorry t as it and we get this thing. Yeah, so that's why, because t needs to be it for this case, that's why it's named as imaginary error function. So in this video we will basically try to see a relationship between these three functions. Yeah, and introduction is just these are just definitions. Yeah, so if integral is from 0 to x of e to the power minus t square dt, in that case this is just orf of x. And if this is from x to infinity, yeah, it was from 0 to x, now if it's from x to infinity, then it's known as complementary error function. And if instead of minus, if we have t square, yeah, we can also see this as e to the power minus of it square. Yeah, so this is because there's I now, that's why we call it imaginary error function. Yeah, now we will try to see relationship between these functions. First of all, these two and then these two. Okay, so now for the first and second, how we can see a relationship between is if we add these two functions. Let's say if we add pi by 2, and the pi by 2 over here is because, let me first tell you the story for that. So if we have an integral from 0 to infinity of e to the power minus t square dt, this is known as Gaussian integral and its answer is root pi by 2. Yeah, so if from 0 to x, if we write this function as root pi by 2 times orf of x, so what happens is orf of the value of orf x will go from 0 to 1 only. Yeah, because if at 0 orf of 0 will just be 0 because there's no area, and at infinity orf of infinity will just be 1 because at that time it's not root pi by 2. Yeah, and in between orf of x will always lie between 0 to 1. Yeah, because these values are slightly less than root pi by 2 because it's just an increasing function. Or I think, did it is it an increasing function or not? Because the area, not the function, the area of this function is increasing, so that's why ultimately it has to reach root pi by 2. That's why in between it will be lesser than this value. That's why uh, it will be a nice property to lie between 0 to 1. That's why it's defined like this. Yeah, now let's try to explore relationship between these functions. Okay, okay, first of all, first two. So we can take root pi by 2 root pi by 2 or common, and then orf of x plus orf c, orf c of x. Yeah, now if we add these two, what will we have? We will have basically integral from 0 to x of e to the power minus t square dt, and then integral from x to infinity. Yeah, now the first one is just area from 0 to x, and this is area from x to infinity, so you can add them as area from 0 to infinity. Yeah, and so this will just be root pi by 2. Yeah, so we can see that this answer is actually root pi by 2 of x plus of complement of x. And now we can cancel the root pi by 2 from both sides, which gives us a nice property that erfc of x is actually 1 minus erf of x. Yeah. So this is a cool property to remember, and this is also the relation between erf and erf complementary erf function. Okay. So now between the first and third. So for that again we can go with this function. Root. Let's begin with root pi by 2 of I of x. Okay. This is e to the power t squared dt, and from 0 to x. So now let's make a substitution. Uh, Let me erase that first. Okay. So now let's make a substitution. Y equals to let us make substitution. Y equals to it. Okay. So that this will be negative. So if with the substitution we will have integral from 0 to ix. Yeah. And then e to the power we will have y by I whole square, and then dy by I over here. Now this will be integral from 0 to ix e to the power, that will be y square by minus 1, so I can write minus 1 over here as well, and that will be dy. 1 by I is minus I. Yeah. Okay, now let me take minus I in the front. Now this is integral from 0 to ix of e to the power minus y squared dy. That's why it will be minus I, and then this is just root pi by 2 times erf of. So if there's ix, it will be ix. Yeah. So basically this variable goes over here, this variable will be here, this variable will be here. Yeah. So if there's ix, we will have ix over here as well. So now we can see that root pi by 2 of or phi x is actually equals to this. Now we can cancel root pi by 2, and that gives us a nice relation that r phi of x plus I r phi of, sorry, okay, this is not r phi, plus I r phi of ix is equals to 0, and that means we can write this as I r phi of ix is equals to minus r phi of x, and then take it to other side. We will have r phi of ix. Now it's minus 1 by I times r phi of x. Okay. So we have this nice relation that r phi of ix is actually equals to I times r phi of x. So we have three nice relations now, and let me talk about one more property of our function that's really helpful. That is just like this one, orf of minus x is actually equals to minus orf x. That means it is an odd function, and for that we can start with the definition. This will be e to the 0 to minus x, since here's minus x, e to the power minus t square dt. Now since this is an even function, yeah, that means okay, so since this is an even function, what can we do? So it will be, or is this an even function? Yeah, this is. Now its graph will be something like this. Yeah. Now its area from x to 0 and 0 to x both will be equal. Yeah, because it's an even function. That's why we can say that this is actually equals to integral from x to 0 of e to the power minus t square dt. Now using the reflection property, this is equals to minus integral from 0 to x of e to the power minus t square dt. Yeah. Now this will just be equals to minus, now this is definition of r of x. Yeah, so we can see that r function is actually an odd function. Now I think this is enough for the video, and the last property that you can try to prove is r of x complement is r of x whole complement. Yeah, where x is a complex number, and you know the complement for complex number, it's just reflection about real axis. Yeah, so I think these are some of the properties and relations that you can know. Yeah, I basically see a relation between orf and orfc, orf and orfi, the definitions, and the orf function is odd, and orf of x complement is orf x complement. So I think you learned quite a lot of things. Yeah, and yeah, I hope it was helpful. Thanks for watching. Look forward to seeing in the upcoming videos too.